question, and this relates to the mirror equations that I've written here. So, can you guys see this in the back? This is kind of dirty. Can you read these? Yeah? Okay. So I'll move this up. Put it at the top. So here, I tell you a concave mirror has a focal length of 42 centimeters, and the image has a size of 10 centimeters, which is formed by this mirror 97 centimeters in front. So what we want to do is we want to figure out, if we know where the image is and we know what the size of the image is, what is the distance to the object, what is the magnification, and ultimately what is the size of the object. Okay? So go ahead and spend some time working on this. So let's go ahead and talk about this one. So we tell you that we have a concave mirror that has a focal length of 42 centimeters, and there's some image that has size of 10 centimeters formed by this mirror, and it's 97 centimeters in front of the mirror. So the first thing that we want to find is what is the distance to the object, okay? So in order to do this, what we can say is we can write down our mirror equation. So 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. Okay. So just a pause about the exam and just general good solution writing practices. Whenever you solve any kind of problem, it's very helpful for us when we're grading it. If you're going to use this equation, write this equation as the first step that you're doing, as opposed to plugging numbers into the equation. Because if you're mixing steps, or you do a couple of steps without writing them out, and you might make a mistake, it's very difficult for us to assess partial credit. Okay, so if I'm solving this problem, and you'll see me do this almost every time that I solve any problem, I always write down what the initial equation is, and we really want you guys to do that as well. Part of the reason is, in some weird scenario, say I'm incapacitated and John's incapacitated, but the class must go on, and so I'm going to have to pick somebody to come up here and explain everything to everybody else. And in me picking somebody, I need to know that what they're going to do is they're going to explain every step. Right? Because if I skip steps, then the other students won't understand. Okay, so imagine when you're writing your solutions on the exam, you're trying out for my job, and hopefully maybe someday one of you guys will replace me, so in like 50 years when I retire or something. Okay, so this was the equation that we start with here, and we know that the distance to the image was given. So this was the 97 centimeters, and we also were given the focal length. So what we want to solve for is the distance to the object, and so what we can do in order to do that is we can move the distance to the image to the other side, and so this is going to be 1 over the focal length minus 1 over the distance to the image. And now what we can do to find what the distance to the object is we can just invert both of these. So we can say that the distance to the object is going to be equal to 1 over the focal length minus 1 over the distance to the image to the -1, and then we can plug our numbers in. So this says that this is going to be 1 over 42 centimeters minus 1 over 97 centimeters inverted, and this gives us an answer of 74 centimeters. Okay? So that's part A. Part B asks, what is the magnification? And so in order to find the magnification, I have really kind of two relationships that I could play with, right? We could use the ratio of the distance of the image to the distance of the object, or we could use the ratio of the height of the image to the height of the object. Now we don't actually know what the height of the object is, so we're forced to say that the magnification M is equal to minus di over do. In this case, the distance to the image was the 97 that we found, divided by the 74 that we just found here. So these are both in centimeters. And very important, there's a negative sign here. Okay? And we'll see what this negative sign means in a moment. But this gives us an answer of negative 1.31. Okay? Now let's talk about what the meaning of the negative sign is and what some different scenarios we can have for the magnification are. So if I have a positive magnification, what does that mean? Not necessarily. It might. It might.
Stays up.
It's upright, right? So if I have a positive magnification, then the image is upright. Okay. Now let's talk about whether it's larger or smaller. So is this one going to be larger or smaller? Just based on looking at the magnification. It's going to be larger, right? And the reason why we can see that is the magnification, the way that you can think about it is it's a scale multiple of the size of the object, right? We could rearrange this equation, right? So we could say that well, that gets to the next part of the equation, but let's look at this. So if we want to find what the height of the image is, we can say that this is equal to the magnification times the height of the object, right? And so if the magnification is larger than 1, this height here is larger than this one, right? Because if I multiply this by 1, these are the same. If I multiply this by something less than 1, this is smaller than this. Or if I multiply this by something that's larger than 1, then this is larger than this, okay? So the last thing, and I actually think that's everything I wanted to say about that so far. So we can already, based off of this, we can kind of predict what our answer should kind of look like for the height of the object versus the height of the image, because we know the magnification is going to be larger than 1. So let's go through the rest of the calculation here and see if our suspicions are confirmed. So we have this magnification, negative 1.31. This is also equal to the height of the image divided by the height of the object. Okay? Now, to find the height of the object, what I can do is I can rearrange this so the height of the object is going to be equal to the height of the image divided by negative 1.31. And if I plug this in with the 10 that I have here, what I end up finding is that the height of the object is going to be 7.6 centimeters with a negative sign, if I just plugged everything in exactly as it is. Now, there's something a little funny happening here, right? Because when we talk about some object having height, so if I take my laser pointer and I put it like this, right? And we had some mirror. We always say that the object is going to have a positive distance and a positive height, right? So think about the positive distance to start with. So what that says is that the object always has to be in front of the mirror, right? So if I have, this is my reflecting surface here, it doesn't make any sense to put this over here, right? Because that would be a negative distance. It's on the back side of the mirror. So it has a positive distance, but we also say that it has a positive height because we're always starting with this upright. What can change is whether the image is inverted or not. The object is always going to be positive. And so when I look at this equation and I see, oh, I got a negative sign for my height of my object, there's something funny going on here. And really, what we want to do then is to say, rather than saying that this is the 10 centimeters as stated in the problem exactly for the height of the image, we need to put in a negative 10. Right? Because we didn't specify whether the image was inverted or upright. What we said was it has a size. So size is just going to be like an absolute value of the height. So really this height of the image is going to be negative 10 centimeters, okay? Which means that this is going to be positive 7.6 centimeters in the end. Okay? Any questions about this? It was a little bit of a roundabout way to explain that because I wanted to talk about why exactly the negative sign was there. Yeah.
So basically the object is always positive.
Right. Both terms for the object for mirrors. When we get to lenses, you can put it on either side, but for mirrors, the distance to the object and the height of the object are always positive. Yeah. Okay. Other questions? Okay. So let's move on to another one. So this one, we have to be a little bit careful, because when we talk about concave versus convex mirrors, when we talk about concave and convex mirrors, where the focus and where the center of curvature is going to change, right? So say I have some object here, and this is some concave mirror, so this is the reflecting side, versus this is some convex mirror, okay? And then this is the reflecting side. So look at the arcs of the circles that I have here. Where is if I labeled where the center of this circle is going to be for each case, where is it going to be in the first case? Is it going to be to the left or the right side of the mirror? It's going to be the left, right? So if it might be anywhere along here if I drew it to scale, but the point is that center of curvature is going to be on the left, focus is also on the left. Now in this case, it's different, right? Because if I look at where the center of if I extended this out to make the full circle, the center of that circle is going to be on the right side, right? And that also means that the focus is on the right side. So when you're working this problem, you have to be very careful with your signs, because when we're saying that something's positive, that means that it's going to be on the same side as the object. And if something's negative, it's going to be on the opposite side of the object. Okay, so go ahead and spend some time talking about this with your neighbor, and then we'll talk about it. Okay, so let's go ahead and do this one quickly. And I noticed that a lot of you guys are studying for the exam, so you're not very focused on doing this. So we'll switch over to talking about the exam material. Gotta give the people what they want, right? So let me solve this problem really quickly, and then we'll come back to finishing these calculations with mirrors after spring break. But just to do this one quickly, what are we told here? We're told what the radius of the helmet is, what the distance from you to the helmet is, and what your size is. And the first thing that we want to do is to find what the distance to the image is going to be. Now we can sketch this. Is this on yeah, you guys are fine. So we have this convex mirror here, and we know that the distance to the radius of curvature is going to be 15 centimeters. So the focus here is going to be 7.5 centimeters. Okay? So what we want to do is we want to apply this equation that says 1 over the distance of the object plus 1 over the distance to the image is equal to 1 over the focal length. So this is going to be 2 meters. And so what we want to do is we want to solve for the distance to the image. So when we do some algebra and rearrange this equation, what we end up finding is the distance to the image is going to be equal to 1 over the focus minus 1 over the distance to the object, inverted. Okay, this is the same algebra I did in the last problem, so just refer to that if you didn't follow that step I just went through. So now what we need to do is we need to plug in the values here, and we have to be very careful, because when we plug in the value of the focus, we need to take into account that you are going to be on this side of the mirror, and the focus is going to be on the opposite side of the mirror. Okay? So what that means is I need to plug in a negative here, and I also need to make sure that I convert my units. So this is going to be 1 over 0.075 with a negative sign, minus 1 over 2, inverted, and when I do this, this is going to be equal to negative 0.26 meters. Okay. Now, what does this say? The fact that this is negative. What does it mean if I have a negative distance to the image? I'm hearing the gears turning. What are you guys thinking?
Front of the mirror? Right, on the right side?
Remember, you're on the right track, but it's actually the opposite. Right. So, left, right side. I was thinking my right side. Yeah, it's on this side. Sorry about that. So, negative distances to images mean it's a virtual image, which means it's on the opposite side of the object, and so it's on this side. Okay. So then what we want to do is we want to calculate the magnification. We say the magnification M is going to be equal to minus di over do. And now here we need to plug in this negative 0.26 meters divided by the distance to the object, which is going to be 2 meters. And so this is going to be equal to, I have an additional negative sign here because it had this negative sign and this negative sign. And this is going to be equal to 0.13. Just 0.13 is the magnification. Okay. So then the last thing that we want to find is what the height of the image is. So to find the height of the image, we say this 0.13 is going to be equal to the height of the image divided by the height of the object. And the height of the object is going to be 1.6 meters. So we rearrange this, and so we say that HI is equal to 0.13 times 1.6 meters. And so this is going to be equal to 0.169 meters, okay? And so let's see if this makes sense. We have 0.169 meters for the height of our image, and we had a height of the object of 1.6 meters. So which one's larger, which one's smaller? Is the image larger or smaller than the object? Smaller, right? Because 0.169 is smaller than 1.6. And let's look at our magnification. Magnification is 0.13, right? So because this magnification is less than 1, that means that the height of the image should be smaller than the height of the object. Okay? Any questions about this? Okay, so like I said, we'll skip ahead now to talk about the exam. So what I want to do is very quickly lay out all of the equations that we have, talk about some of the right-hand rules. I posted a video that does this on course networking as well, so you can look at that tonight while you're studying. But I'll walk through it here as well. Now, there are also a couple of equations that are important to remember from the last test. So let's talk about that first, okay? So some equations that we had from last test, you remember that I drew this table, and this related the force to the electric field, to the electric potential, to the potential energy. And there were some equations that related those quantities to each other. So the first equation said that the electric force acting on a charge is going to be QE. The electric field is going to be equal to the negative change in electric potential divided by the change in distance. The potential energy is going to be equal to Q times V, and the force is going to be equal to the negative change in potential energy divided by the change in distance. Okay, so we're not going to concern ourselves with what these are in particular for this exam, but be sure that you understand how I can go from, if I give you an electric field and there's a charge with some magnitude, say it's an electron, right? What's the force going to be acting on that charge? And also, if I tell you that I have some charge that moves in some electric potential, what is the change in potential energy? And so why would we care about change in potential energy? What does that allow us to do? This is something that came back from last semester, yeah.
Figure out velocity and distance.
Right. By what method? What's the overarching idea that allows us to do that? Conservation of energy, right? So this equation is very important for when you're conserving energy for an electrostatic system or electrodynamic system. When you have some charge that's going to move in some potential and I want to find some velocity. So keep these four equations in mind. There might be some calculations that you'll have to do that will involve those. The other things from last test you need to make sure that you remember are all of the equations that relate circuit elements, okay? So Ohm's law, V is equal to IR, P is equal to IV, which is the power dissipated by some circuit element, which can also be written as I squared R, and can also be written as V squared divided by R. And then your capacitor ones too. Q is equal to VC. Okay. Keep these equations in mind, and you won't be expected to go to the same lengths to do calculations with any of these things that we did on the last exam, but you might need to apply some of these equations in order to solve things on this one. Okay. So that's the stuff from the last exam that might show up again here. Now the new material, the first thing that we want to talk about is what's called the Lorentz Force Law, and that's the magnetic portion of the Lorentz Force Law, or the general part, and this is, I don't know if the book even talks about the Lorentz Force Law the way that I do, but there's a reason why I do, and it's because what the Lorentz Force Law says is I can write some general equation for what the force is acting on a charged particle in the presence of both an electric field and a magnetic field. This is what the Lorentz Force Law says. And it's a very powerful equation because it allows you to say how a particle is going to move or how its movement is going to change in the presence of both an electric field and a magnetic field. So when you look at this equation here, this actually encapsulates the same information that I had up here, only it also includes what happens with the magnetic field. Okay. Now we talked about this first part on the last test, and I referenced that up here. The new part was talking about the magnetic force on a charged particle that's moving. So that's just the second part. Okay. And this is where we started getting into talking about the right-hand rule. So here, whenever we see some equation with some cross product, and in fact we did this last semester too when we talked about torque and angular momentum, whenever you see an equation with a cross product, that should indicate to you that you need to use the right-hand rule in some fashion. And the way that you're going to do this is what I called right-hand rule 1 in the video. And that's to say I'm going to point my fingers in the direction of the velocity. I'm going to curl them in the direction of the magnetic field, and this is for your right hand. So fingers of right hand in the direction of the velocity, curl them in the direction of the magnetic field, thumb points in the direction of the force. Okay. Now this right hand rule 1 has another use, and that's to find what the force is on a wire. So the magnetic force acting on a wire is going to be equal to the length of the wire times the current crossed with the magnetic field. Okay. And again, you can see why the right-hand rule is going to manifest itself the same way. When you look at these two equations, I have this vector cross this vector is equal to this vector. This vector cross this vector is equal to this vector, right? I could go to even more lengths to write equations like this to say, okay, if we wanted to talk about something from last semester, L is equal to R cross P, right? When we talked about angular momentum last semester. The direction of the angular momentum can be found by putting my fingers in the direction of the radius vector or the distance vector, and then curling them into the direction of the momentum, thumb points in the direction of angular momentum. Okay. Anytime you see any equation that looks like this, that's the way that you're going to apply the right-hand rule. Okay. So we'll get rid of that one from last semester. Okay. Second way you can apply the right-hand rule. So this is what I called right-hand rule 2. This is to find the direction of a magnetic field produced by a current carrying wire. So the associated equation says that the magnetic field is going to be equal to the permeability of free space times the current divided by 2 pi times the distance away from the wire that you're making your measurement of the magnetic field. Okay? Now the way that this one goes, I have some current moving in a wire. I want to find what the magnetic field is on both sides of this. And so what I do is I take the thumb of my right hand, I point it in the direction of the current, and I curl my fingers in the direction the magnetic field points. So we can see on your left side, this is going to be pointing out over here. And we remember this notation for out, and then it's going to be pointing in here, right? Because the magnetic field around this wire, if the current's going up like this, it's going around like this, right? And that's what our second right-hand rule tells you. Thumb in direction of current, curl in direction of magnetic field. Okay. Third right-hand rule. This one says, if I have some magnetic field that's produced by some current in a loop, I can find what the direction of that current is going to be by taking my thumb and pointing it in the direction of the magnetic field, and then my fingers are curling in the direction of the current. So that means in this case, if this loop is producing a magnetic field that's going up, thumb in the direction of the magnetic field, curl in the direction of the loop, and so that says that the current is going to go around in this direction. Okay. Now you can do the reverse too. So if I say I have some loop, and let's give this a current going this way. I want to figure out what the direction of the magnetic field is produced by the current going around this loop. I can take my right hand, have my fingers going in the direction of the current, and it curls this way, and so my thumb is pointing down. So this is the direction of the magnetic field. Okay? So question? No? Some things to be careful of and to keep in mind. These two right-hand rules look a lot alike. You're having a thumb in a direction, you're curling your fingers in a direction for the third vector, right? You want to make sure that you separate these, because for right-hand rule 2, my thumb's in the direction of the current, fingers curl in the direction of the magnetic field. And for right-hand rule number 3, my thumb is pointing in the direction of the magnetic field, and my fingers are curling in the direction of the current. So where my thumb points and where my fingers are curling is reversed. But if you're thinking about the physics, what's happening in these situations, it'll be clear to you, because I know for this case of some current moving up in this wire, the magnetic field should go around this way. And so the curling of the fingers has to be associated with the direction the magnetic field goes around this. And same thing with this one, right? The thing that's going around in this case is the current. So my fingers are curling in the direction of the current, thumb points in the direction of the magnetic field. The other thing that you need to be careful of is there will be questions like, let me not give you what's on the exam, so let me think. I'm sorry. Okay, yeah, this is fine. Okay, so this has some current. This is some loop of wire that has some, let's say some length of L and some height of H. And let's say, for instance, I'm pulling it this way. Okay, we want to find what the force is acting on this. Now, there's a couple of different ways to do this, but ultimately you're going to need to apply a couple of these right-hand rules, right? Because the first thing I need to do is I need to figure out what the direction of the magnetic field is produced by this long wire. And then what I need to do is I need to say, okay, well, I'm pulling, let's say this is moving with some constant velocity and I'm not pulling with the force. This is moving some constant velocity. And then I need to figure out what the direction of the induced magnetic field is in this one. And then once I have that, I can find what the current is. And once I have the current, I can find what the force is. Now, the thing that you need to be really careful of with these kinds of problems is we really have two magnetic fields, right? We have one that's produced by the wire and one that's produced by the loop. You need to make sure that when you're trying to find the force acting on this loop, you're using the current in the loop and the magnetic field produced by the wire. You never want to mix it so that you say, or it should always be mixed in a sense that you're doing something from this acting on this. You don't want to say, I know the direction of the induced magnetic field here, I know the direction of the induced current, and I'm going to use that magnetic field to find what the direction of the force is. It always has to be one object acting on the other. It can't be what an object might hypothetically do to itself. Okay? Any other questions about this? I think that's really, I mean, it doesn't seem like a lot, right? There aren't really a lot of equations for this test. Yeah? Example of this? I actually have examples for you guys to work on, and then I'll come around, and if you're having problems with that, I'll talk to you independently. Okay. Other questions? Yeah. One more time?
Could you repeat the first one?
Sure. And let me go into more detail with this. So, first right-hand rule. Let's think of a couple of scenarios here. Velocity, magnetic field, velocity, magnetic field, force, and velocity. Okay, and then let's do force and magnetic field. Force and magnetic field. Okay, and what you can see is like, if you run out of problems to solve, make up some of your own, right? I just made up 4 problems on the fly, but you should, when you're thinking about these equations and what permutations of variables can be given, you should be able to think, okay, well, I can give you these two and change what the directions are. I can give you the force and the velocity. I can give you the force and the magnetic field, and make sure you're able to do that. Okay, so let's look at how we're going to apply right-hand rule 1 to these cases. Okay, so fingers in the direction of velocity, right? Everybody, right hand. Okay, fingers in the direction of velocity. Curl in the direction of the magnetic field. Don't hit your neighbor. It's not very nice. Okay. So fingers in the direction of velocity, curl in the direction of the magnetic field, thumb points in the direction of the force. Now the other thing that I didn't say here, I'm assuming these are all positive particles, just for the sake of simplicity. What's going to be different? What's going to be different if these are negative? The force is flipped in direction, right? So V cross B is out for the positive charge, but if it's a negative charge, it's the opposite direction. Okay. Second case. Everybody right hand. This is easier for me because I'm facing this way. Fingers in the direction of velocity. Curl in the direction of the magnetic field. Thumb in the direction of force. Force points down. Okay? Okay. Now, this next one is a little bit different because I don't tell you what the magnetic field is. We need to find what the magnetic field is based on what the force is and what the velocity is. Okay? But what do we know? What's the direction my thumb should have to point here? Why?
Because it's force.
Right. Force is always going to be, when you talk about right-hand rule 1, force is always the direction your thumb points. Okay? So we fix our thumb going down. And then I'm kind of free to rotate my hand around, right? But my fingers need to be pointing in the direction of the velocity. Right? So thumb is fixed down, fingers pointing in the direction of velocity is pointing this way. Again, I chose nice ones for me, but I'm allowed to move around. Right? So fingers point this way. What's the direction my hand needs to curl? That way, right? So that means our magnetic field is pointing that way, okay? Last one. I tell you what the direction of the force is and what the direction of the magnetic field is. What does the direction of the velocity have to be? So, thumb in the direction of force. Now this one's kind of weird because what I need to do is I need to have my fingers curling in some direction so that that direction is down, right? So I'm fixing my thumb in the direction of the force. I need to rotate my hand in such a way that when I curl my fingers, they're going to be down. So that curls down, and then I uncurl it, right? Just curl down, uncurl, velocity is this way. So this has the velocity that way. Okay. Now, this is just the right-hand rule 1 for the charge moving in the presence of a magnetic field. But like I said, because this equation and this equation are basically the same equation except for what these parameters are and these parameters, the way that you perform the cross product is exactly the same, right? So if instead I tell you I have some wire with some current, and we want to find what the direction of the magnetic field is. Say we have this case, we have I and let's say B points down. Right? What's the direction of the force on this one? This one is going to be pointing in, right? Fingers in the direction of current. So that's the only thing that changes here. The only thing that changes is when I'm applying the right-hand rule for this equation, the fingers are in the direction of the current instead of the velocity. Right? Fingers in the direction of current, curl in the direction of the magnetic field. This force is going to be pointing in. Okay? Any other large group questions? Okay. So can you guys help me pass these out? So you guys are, I'm giving you a worksheet that has a lot of practice problems on it, but you're also free to work on whatever you feel will help you if it's the, if it's a practice